Hello, everyone, and welcome. My name is Andrej Risteski. I'm from Carnegie Mellon University. I'll be talking about a joint work with Rong, Holden Li, and Jianfeng, all at Duke. Our paper is about efficient sampling from the so-called Bingham distribution. To set the context a little bit, let me set up the problem of sampling from distributions that are specified up to some constant of proportionality. Namely, the problem here is to sample from a distribution p of x proportional to e to the minus f of x, where we're given access to the function f, either explicitly or through some kind of oracle, so maybe value or gradient oracle. This problem is quite natural as it shows up in the so-called latent-variable paradigm, which is a common paradigm in unsupervised learning. The idea here is that we're going to model our data as being somehow simple, conditioned on some unobserved or latent variables. For instance, imagine we want to model the joint probability of diseases and symptoms in patients where the diseases are latent and the symptoms are observed, and we factorize it as the probability of the diseases times the probability of the symptoms given the diseases, where both of these factors have some simple explicit parametric typically form. The task of inference then is the following. We're given a patient exhibiting some symptoms. We want to sample the posterior distribution over the diseases given these symptoms. Where the difficulty here lies is that we know that by Bayes' rule, this posterior probability is proportional to the joint probability of the diseases and the symptoms, which has some simple and explicit form, albeit there's some normalizing constant here, which unfortunately involves marginalizing over the possible combination of diseases that a patient can have, which makes the problem hard. On the side of applications, being able to sample from such posterior distributions turns out to have lots of applications for these latent variable models. For instance, for diagnostics, if we can sample from these posteriors, we can evaluate the fit or the likelihood of the model. This is typically how we use these models. So for instance, if we have this disease symptom model, we would like to, given a patient with some symptoms, check what's the probability of some disease like flu or heart attack. In more complicated incarnations, this can get substantially more complex. Maybe we have a model that tries to map between modalities, and we give it a description of some picture, so a bird with a particular crown and color of their feathers, and we want the model to generate samples that look like this description. This problem exhibits a natural dichotomy, depending on whether the function f is convex or not. When the function is convex, these are called log-concave distributions, and we have provably efficient algorithms. So one canonical algorithm is the so-called Langevin dynamics, which is a kind of analog of gradient descent for optimization. But as a modeling assumption, this is practically restrictive because the distributions are unimodal. On the other hand, if we drop convexity, in general, the problem is going to be sharply hard. This is a kind of parallel to what happens in optimization, where if we want to minimize a function f, if it's convex, doing so is easy. We can run gradient descent, and we know that all the local minima are global. If we want to minimize an arbitrary non-convex function, in general, it's going to be NP hard. The particular problem that we're going to focus on here is sampling from a distribution P, which is defined over the unit sphere in d dimensions, and it has the form P of x is proportional to the exponential of x transpose ax for some matrix A. In terms of applications, this distribution shows up in many domains. Oftentimes, it's used for modeling directional statistics. So this happens in paleomagnetic data analysis, in computer vision, and even in some applications in differential privacy. On the more statistical side, it appears fairly natural when we wish to sample from certain posteriors in noisy rank 1 matrix inference problems. To flush this out a little bit, imagine that we have a vector x, which is sampled from the uniform distribution over the d-dimensional sphere, and then we're outputting a noisy observation in the form of a matrix y, which is xx transpose plus some noise n sampled from an appropriate Gaussian. For such an observation y, if we want to look at the posterior distribution over the x given the observation y, it turns out to have the form of a Bingham distribution. In terms of the difficulty of sampling such a problem, it turns out that standard techniques, for instance, running this canonical Langevin dynamics in a kind of manifold incarnation, so over the unit sphere in d dimensions, will yield in general an exponential time algorithm. There's some prior work in the statistics community by Kent et al., who proposed a rejection sampling-based algorithm where the proposal distribution is fairly natural. It's a renormalized Gaussian, meaning you sample from an appropriately chosen Gaussian, and you renormalize your sample to have unit norm 1 for it to lie on the unit sphere. However, they only give theoretical guarantees in the so-called low temperature limit. So for sampling from Bingham distributions with the matrix A being beta A, where beta is going to infinity. There's another very related work by Moitra and Risteski, which proposes a Langevin dynamics-based algorithm for the noisy matrix inference problem that I mentioned, which, however, only works for small enough noise levels gamma. On the flip side, it works for an arbitrary rank R rather than just the rank 1 case that we consider here. So with that in mind, let me tell you what our result is. So our result is a polynomial-time Las Vegas algorithm for sampling from the Bingham distribution. More precisely, let's assume that our matrix, that the matrix A is symmetric, and this is easily seen to be without loss of generality. And let's denote its maximum and minimum eigenvalues as lambda max and lambda min. We give an algorithm for sampling from P of x, which runs an expected time polynomial in lambda max minus lambda min, and the dimension d. Now, let me give you a little bit of an idea for how the proof works. And the main idea is a kind of polynomial expansion. So let me flesh this out a little bit. First, we're going to reduce our problem to sampling from the Bingham distribution where the matrix A is diagonal. How do we do this? Well, if your matrix A has the form UDU transpose, if that's its single value decomposition, given a sample from P of x proportional to exponential of x transpose dx, so when the matrix is diagonal, if we output U times x, this is in fact going to be a sample from P of x proportional to exponential of x transpose ax. So that's easy enough. Second component is we're going to do rejection sampling using as a proposal distribution Q of x of the following form. It's going to be proportional to x transpose I plus d over nx to the power of n for sufficiently large n. So I need to tell you first why this is a useful proposal distribution and how we can sample from this proposal distribution. Towards how this is useful, this is essentially a Taylor expansion. So if we take the logarithm of the expression for q, we get n times logarithm of x transpose I plus d over nx, which is using the fact that x is a unit norm vector, it's n times logarithm of 1 plus x transpose d over nx, which using kind of the approximation of log of 1 plus x is approximately x for small x, should approximately be equal to x transpose dx. Making this formal, we can show that for sufficiently large n, p and q will be multiplicatively at most a constant factor away. Now, how do we sample from such a proposal distribution Q? As usual, the rub lies in the kind of partition function being not explicit, but the reason why we can actually do it here is that we can basically do it by proceeding in a coordinate by coordinate fashion using marginalization and just inverse, like simple inverse transpose sampling. And the main idea here is that the partition functions of these kinds of distribution, which will look like integrals over the unit sphere of quantities like x transpose dx to the power of n, can in fact be calculated in time polynomial in n and d. And the reason why this works is essentially this problem can be reduced to calculating moments of a Gaussian, of a multivariate Gaussian. And for these, we can write down some recursive formulas via dynamic programming, so we can do it in time polynomial in n and d. Furthermore, if we proceed in a coordinate by coordinate fashion, once we sample a particular coordinate, the conditional distribution on the remaining variables has still the form, p of y of the same form. So p of y is proportional to y transpose times I plus some d tilde over ny to the power of n. So we can just proceed recursively. Towards some open problems, it would be interesting to see if we can handle the rank k case. So here we only handle the rank 1 case. The problem has a natural rank k formulation. It would also be nice to see if we can prove comparable polynomial-time runtime guarantees for some more canonical algorithms like Langevin dynamics-like algorithms or Gibbs samplers. And finally, this polynomial approximation technique for unnormalized densities seems rather generally applicable. So it would be nice to see if we can find more applications of this technique. Thank you, and please ask any additional questions during the Q&A.